Hello again, all. This is another in my series of videos on computer systems. And this one will be continuing Module 7, and this will be Part 2, our second and final part of the module. And in this one, we're going to be focused on the operating systems book. We're going to cover part of Chapter 10, and what we're going to talk about in this video is real-time scheduling. So, in real time systems, the operating system, and particularly the scheduler, is maybe the most important component. And we're going to be talking about control of laboratory experiments, process controls, robotics, air traffic control, telecommunications. We could be talking about things like safety systems like airbags and anti-lock brake systems in cars. This stuff is important. This is stuff where we have to do things within a certain very, very short time frame, or lots of money can be lost and even lives could be lost. So if your airbags don't deploy until after the crash is already over, that doesn't help, right? We could actually end up costing human life or injuring people very badly if we don't implement these systems properly. Now, the correctness of the system depends not only on the logical result of the computation, but also in the time at which the results are produced. So even if we do what we're supposed to do, again, if the car detects a crash and deploys the airbag, logically, that's what's supposed to happen, but it's still failed if it doesn't happen quickly enough. So tasks or processes attempt to control or react to events that take place in the outside world. These events occur in real time, and tasks have to be able to keep up with them. We're moving outside of just the realm of inside this computer to we have to actually interact with the real world, and the real world can't block and wait, right? We have to actually react within a timely manner if we're going to interact with the real world and do what we're supposed to do. Now, we have a couple terms that we want to be familiar with. We have hard and soft real-time tasks. A hard real-time task is one that must meet its deadline. Otherwise, it will cause unacceptable damage or a fatal error to the system, right? So this is one, it's a hard deadline. It's no matter what, this thing has to meet its deadline. A soft real-time task has an associated deadline that's desirable, but it's not mandatory. It still makes sense to schedule and complete the task, even if it's past its deadline. So this is stuff that we'd like it to happen with a certain speed, right? With a certain, in a certain short amount of time. But unlike a hard real-time task, which if it misses its window, there's no point in running it, with a soft real-time task, even if it's going to miss the deadline, it still makes sense to actually go ahead and run the thing. We also have periodic and aperiodic tasks. Periodic tasks happen once per period. So if we're talking about T as our period, they're going to happen once per period T, and they happen exactly T units apart. So this is something that just keeps on happening, every so often, forever, basically. Aperiodic tasks have deadlines by which they must finish or start, and they may have a constraint for both start and finish time. All right, so it might have to start by a certain time and finish by a certain time. That's our aperiodic tasks. Now, characteristics of real-time systems. They have 5 general areas. We've got determinism, responsiveness, user control, reliability, and fail-soft operation. And we'll chat about what these things mean as we move through the slides. So let's start right out with determinism. We're concerned with how long an operating system delays before acknowledging an interrupt. Operations are performed at fixed predetermined times or within predetermined time intervals. So when multiple processes are competing for resources and processor time, no system is going to be fully deterministic. All right, so the extent to which an operating system can deterministically satisfy requests depends on the speed at which it can respond to interrupts, right? We've got things like clock speeds and, just how fast can this thing actually process an interrupt, and whether the system has sufficient capacity to handle all the requests within the required time. So again, if we've got multiple things going on, if we get too many interrupts, at the same time, well, we might not have sufficient capacity to handle all of those. So, is it determinism? We're talking how fast can this thing respond to, can it actually acknowledge an interrupt when it comes in? Responsiveness, now this goes together with determinism, and this makes up the response time to external events. Again, this is critical for real-time systems, right? Because we're interacting with the outside world, so we have to know what's going on. So what responsiveness is how long after acknowledgement it takes an operating system to service the interrupt. So that's why it goes hand in hand, right? The first one, when an interrupt comes in, the first thing we have is the determinism, which is how long does it take for the system to acknowledge that interrupt and know that it's there, to actually process the fact that an interrupt has occurred. Then the responsiveness kicks in, and this is how long after that acknowledgement takes place it takes to actually service that interrupt. So this includes the amount of time required to initially handle the interrupt and begin execution of the interrupt service routine, the amount of time required to perform the service routine, and the effect of interrupt nesting. Moving on to user control. This is going to be a lot broader in real-time operating systems than in an ordinary operating system. It's essential to allow the user fine-grained control over task priority. So the user should be able to distinguish between the hard and soft tasks and to specify relative priorities within each class. So we might allow the user to specify whether we do paging or process swapping, what processes always have to be resident in main memory, what disk transfer algorithms are going to be used, and we'll talk more about those in Module 9. What rights the processes and various priority bands have, right? So we can't kind of just rely on automation. We can't just let the system kind of automatically take care of everything for us like we do in a lot of systems. Real-time systems, again, we're dealing with the outside world. We have all of these, both hard and soft real-time tasks that we've got to deal with. So the operating system has to let the user really, really get in there and tweak things so that we know we've got everything set up so that hopefully we can actually respond to all these things within the required times. Now, our next thing is reliability. This is more important for real-time systems than non-real-time systems. Real-time systems are going to control events in real time out in the real world, so degradation of performance could have all sorts of problems, which I already talked about a couple slides ago, right? We could lose a bunch of money, we could damage equipment, and even up to we could end up with loss of life if certain systems end up not performing the way they need to perform. If it takes too darn long to, again, deploy the airbag or apply the anti-lock brake system or start the fire suppression system, right? We could, people could die. We could end up with severe injury or loss of life if we don't have a reliable system. If we can't count on our system to do what it's supposed to do all the time. And finally, we want to talk about fail-soft operation. Now, this is a characteristic that refers to the ability of a system to fail in such a way as to preserve as much capability and data as possible. All right, so we don't want a failure to look like the whole thing just blows up or the whole thing just shuts down and we lose everything. We would like to hopefully keep things in such a way that failures are as soft as possible. Now, an important aspect is stability, right? It's stable if the system will meet the deadlines of its most critical, highest priority tasks, even so if some less critical stuff are not always met. And this goes back to allowing users to kind of set those priorities, right? If I've got 5 things that are absolutely critical, I want to make sure that I have the ability to tell the system that. So that even if we lose some less critical stuff, those really, really highest priority tasks are going to keep working the way they should. So in order to make this happen, we tend to see a stricter use of priorities than in an ordinary OS, right? We have preemptive scheduling designed to meet real-time requirements. Interrupt latency is bounded and fairly short, right? That gets back to our determinism and then eventually our responsiveness, right? We want to make sure that we process those interrupts fast. and we want more precise and predictable timing characteristics than a general purpose OS, right? Again, on a desktop, it might be annoying, but if things kind of freeze up for a sec, or you get the little spinning beach ball, or, the little circular thing on Windows, whatever it is, it's annoying, but if that happens here and there for a few seconds at a time, it's not really that big a deal. In a real-time system, it's a big, huge deal. So now that we've talked about these characteristics, let's talk about real-time scheduling. Let's get into the nitty-gritty of what this whole video is about and talk about the scheduling approaches. Now, those depend on whether a system performs some kind of schedulability analysis, and if it does, whether it's done statically or dynamically. Right? So do we sort of get the information right up front, or does it happen as things change? And whether the result of the analysis itself produces a scheduler plan according to which tasks are dispatched at runtime. So let's take a look at some classes of real-time scheduling algorithms with that idea in mind. We have static table-driven approaches. This performs a static analysis of feasible schedules for dispatching, and the result is a schedule that determines at runtime when a task has to begin execution. In a static priority-driven preemptive approach, the static analysis is performed, but we don't actually draw up a schedule, right? We perform the analysis, we figure out what all the metrics are, but we're not actually going to plan a schedule from that. The analysis is used to assign priorities to tasks so that we can use a traditional priority-driven preemptive scheduler. And that's the kind of thing that we talked about in the first video of this module. In dynamic planning-based approaches, feasibility is determined at runtime rather than offline prior to the start of execution, right? With a static approach, we kind of know what processes, what kinds of processes we're going to be dealing with, and we can do that offline to get that analysis in our hands to figure out the rest of it. In a dynamic planning-based approach, we're going to do it at runtime. We're just going to do the whole feasibility analysis right then and there. And one result of the analysis is a schedule or a plan that's used to decide when to dispatch the task. For dynamic best effort approaches, we don't do any kind of feasibility analysis, right? We're just going to save the time on that. The system tries to meet all the deadlines and just aborts any started process once it misses a deadline. Now, another thing that we want to be aware of is something called deadline scheduling. Real-time operating systems want to be able to start real-time tasks as quickly as possible and emphasize rapid interrupt handling and task dispatching. Right? We want to know when something happens in the real world as quickly as possible, and we want to make sure that we can react to it as quickly as possible. We want the system to become aware of things that happen out there in the real world as quickly as we possibly can. But in a lot of cases, real-time applications aren't concerned with sheer speed. It's not just about immediately reacting to every little thing that comes in, but it's about completing or starting tasks at the most valuable times. So again, if we think about some kind of control system, when something happens, maybe something fails, maybe we just need to do some kind of manufacturing tasks, it's entirely possible that we get several different tasks, several interrupts kind of near the same time, but these are going to have different priorities, right? It might very well be that I need to do certain things just as quickly as possible. Some things might be about sheer speed, but other things might just have to happen within a couple seconds, right? They might have to happen within some kind of time frame that's a little less restrictive. So we want to focus on, we want to be able to prioritize those things and run those tasks in the order that in which they're important. So setting priorities can provide a crude tool. They don't capture the requirement of completion or initiation at the most valuable time, but they can help, right? Then we can also, though, put some things in place where we're going to use various kinds of information for deadline scheduling. So we'll use ready time, the time the task becomes ready for execution, the starting deadline, right? This is the time the task has to begin. We can use a completion deadline, the time it has to be completed. Processing time, we got to keep track of that, right? We have to know how long it's going to take to execute the task to completion so we can make sure that we can set our starting and completion deadlines properly. We need to know our resource requirements. What resources are required by the task while it's executing? Again, priority Now notice, like I said, priority, in other scheduling approaches, we might only use priority. In this case, priority is just one of several different bits of information that we're going to use to figure out how we're going to schedule things. We also want to have some kind of subtask scheduler. A task might be decomposed into a mandatory subtask and an optional subtask. So, for a real time system, when it's important that things get done on time, I might need to decompose an overall task and just get the mandatory subtask done. If I can't if I can't find the time to schedule in the optional subtask around other priorities. Now, just like in part 1 of this module, let's point out some tables in your book that will help you kind of understand how various real-time scheduling algorithms work. The first one is table 10.3. This is an execution profile of 2 periodic tasks. Now remember, periodic tasks just happen once every time period t, and they just keep on happening. So you might have, you will have process A, a first instance, a second instance, a third instance. It's just going to keep on coming, right? In this case, 20 time units. Right? We can tell that because the arrival time for the first one is 0. The next one is 20. The next one is 40. The next one is 60, and so on. That means the ending deadlines are basically the start of when the next instance of that process needs to start. And in this case, that processes have an execution time of 10. So that means that the one that arrived at time 0, we've just got to find 10 time slices to dedicate to that process within the first 20 time slices, right? So I've got to just figure out how am I going to execute the first instance of process A all the way through between time 0 and time 20. The next one arrives at time 20, and I got to figure out where to find 10 time slices to execute that one all the way through between its arrival time at time 20 and its ending deadline at time 40. Same thing applies to process B down at the bottom of this table. The first instance shows up at time 0. Now this one takes 25 time slices to run, but we've got an ending deadline of 50. So that tells us 50 minus 0, that's our time period t. So the next one will arrive at time 50, and we got to find 25 time slices between then and the ending deadline at time 100 to execute the second instance of B. Now, the next table I'd like to draw your attention to, it's actually figure 10.5, and this shows you how those periodic tasks are going to get scheduled under different approaches to scheduling, under different scheduling algorithms. So, for example, with fixed priority scheduling, process A, or an instance of process A, is going to have priority. So A1 and B1 arrive at the same time. We can see up at the top at the arrival times and execution times and deadlines, a section right up at the top of the table. A1 and B1 arrive at the same time, but A has priority, so A1 is going to run, and actually that ends up running till it's done, right? We run the whole 10 of that, and then B gets 10 time slices to start getting through its execution. But at that point, A2 arrives. At time 20, A2 arrives, and A has priority. So A2 is going to run till it's done, and then we can try some more of B1. And now we've run 20 time slices of B1. But at time 40, A3 arrives, and A3 runs for its 10 because A always has priority. But we have now hit time slice 40, right? Or time slice 50. B2 arrives, and we just missed B1. We did not find 25 time slices within the deadline for B1 for it to run all the way through. Now, as we continue on, though, B2 arrived. We don't have a new A yet, so B2 gets 10 slices. Then A4 gets 10 slices. B2 gets 10 more slices. A5 arrives, and it gets 10 slices. But, we're still within the... We only have 5 more slices of B2 to complete it, and we're still within its deadline, so B2 actually does manage to complete. So this shows you an example of how, based on these deadlines, we might actually miss tasks. We might try to run a task in time, but we sometimes we're going to miss, and we want to make sure that we're aware of that. And that we plan things out. Again, we're going to have this control, so there's going to be some kinds of processes that just can't be missed. We need to figure out a way to apply one of these scheduling policies such that the really important high priority stuff ends up always executing properly. Now you can see that ends up being different if we do fixed priority scheduling with B having priority. In that case, the same kind of thing applies. B1 and A1 arrive at the same time, so B1 has priority, so B1 is going to run all the way through, but we're going to miss A1 completely. We never even had a chance to start A1 by the time its deadline expired. So we can follow these along and make sure you understand those. So, work your way through this table and make sure you understand how this maps to the table 10.3, this periodic tasks and the way they're coming in. Table 10.4 shows you an execution profile of 5 aperiodic tasks, right? That's the other kind we have to deal with. So in this case, it looks a little more like what we've seen in the first module. We've got processes A through E, different arrival times for all of them. Each of them has, in this case, an execution time of 20, but that doesn't mean that that's always going to be the case. That just this example, each one has an execution time of 20 time units. And each one, in this case, has a starting deadline. So we're going to focus on when these things have to start by when we schedule them out. And then figure 10.6 shows you how these things get scheduled differently based on different approaches. So up at the top, we have our arrival times and our starting deadlines. And then for each earliest deadline with unforced idle times, and first come, first served. And these are all very straightforward. They're just described in the text. So I'll leave you to just read through those. But again, study this table with respect to the table of aperiodic tasks and their starting deadlines, etc. So we can see exactly how these things work to schedule things out. And again, notice that with earliest deadline, we're going to miss process B. With first come, first serve, we're going to miss process B and process E. So again, these are not perfect. We may very well end up missing tasks when we use these different approaches. So for this video, part 2 of module 7, we want to make sure we can describe the priorities of real-time scheduling, that we can describe synchronous task scheduling, and that we can describe asynchronous task scheduling. And again, go back through those tables, through those task profiles, and those figures that show you how the different algorithms lay those things out and schedule them out. Be sure to work your way through those. You should just be able to work through those examples and kind of get an understanding of exactly how those are working. So do that and make sure that before you move on, you work your way through those examples and understand how those are going.